Okay, thank you very much. And it's so good to be able to participate here. And you have an excellent program, and also to see the progress of Cosmos and now the possibilities and already starting experimenting and so on. And I think that is very important and extremely good, because even if 5G now is commercially deployed, it's the first version, and of course it will continue to evolve, and making it definitely possible to include new opportunities, new findings, and fine-tune and so on. And also I think now when we see a little bit the 6G horizon coming up, even if it's far down the road, what I expect is that as 5G evolve, it will of course follow and be a little bit of a precursor to things that will come in 6G. So therefore I think this experimenting and learning now on 5G is very important, and so good to see. And Cosmos is of course a splendid opportunity. So what I will do is to give a little bit my views on what opportunities and challenges we have with 5G, and especially with millimeter wave focus. So starting out a little bit then, what are the main thing and main challenges that we will face now when we go up to millimeter wave? And here I go down to basics and link budget reasoning, and comparing now with, we picked 1.8 gigahertz as being representative for already existing 4G deployments. And then what happens if we go to midband and then high band? And starting out then, of course, the output power, that is one key variable here. And going from 1.8 up to midband, that's basically, you know, we can rely on that we can provide the same amount of power. But if we go to millimeter wave, we see that now, and we call this typical, and that should be interpreted, that is a little bit where industrialization maturity is right now, or maybe even tomorrow. So that is what is meant with this typical here. So going to millimeter wave, we see that we have difficulties keeping up the power. So that means -10, -15 dBs loss in the link budget. Then of course when we can come to the antenna gain, and now we're introducing beamforming both on midband and high band, then we see that here we will of course have a positive contribution to the link budget. So typically maybe 9 dB for midband and 15 dB on high band. Then of course we come to the propagation part, and if we start with the outdoor propagation loss, so that is basically only the propagation itself. There we don't see that there is so much big difference going up in frequencies. So for certain scenarios there is basically no difference from midband if you go to millimeter wave. But of course for millimeter wave, the higher we go, the more diffraction kind of properties we lose. So of course in non-line of sight scenarios relying on diffraction and so on, there we see a lot loss. So here we estimate, yeah, maybe up to 7 dB loss. Then of course we come to the outer to indoor and the penetration loss, and there of course well, we see first of all a large variance, so depending very much on the material, buildings and so on, but not so much on midband, and high variation on the high bands. Then of course on the device side, there we also see some possibilities as frequency goes up to actually also do beamforming and rely on antenna gains. So here we assume that midband maybe we can rely on 6 dB antenna gain and beamforming gain, and on the high band maybe up to 9 dB. So that's positive of course. And then of course at the bottom there we have basically the effect of the antenna sizes. So this is basically the 20 log frequency. So here it is of course a loss. On midband it be 1.8 to 3.5, that's 6 dB, and 1.8 to 28, that's 24 dB. So if we summarize that, we see actually that on midband we can actually provide a better link budget than on 1.8. But then of course here comes a little bit of the challenge. If you look at the millimeter wave, if you count the most what to say, optimistic assumptions, you have still an 11 dB degradation, and up to 42 if you take the worst case and sum them up. So then of course the question is, what can we do about this? And that indicates a little bit challenges, but also some opportunities here to improve this one. So first of all, output power, that we need to work with. So, and that is of course a lot on PAs, materials, also cooling efficiencies and so on. But to cramp up the power, that is of course important. Then on the propagation, that is of course more physical properties, but here of course we can work with deployments and different other ways to overcome the challenges on the propagation side. And then we have of course the antenna gain and the beamforming that we also can improve. So continuing along a little bit on the beamforming, yeah, I guess this is nothing new. We come from a situation where we have fixed antennas, sector sites normally at the base station, and the devices, they are trying to have as uniform antenna pattern as possible. And on midband, normally we do the beamforming more on the infrastructure side. But then when we go to the high band, then we need basically to do beamforming both at the base station side and also on the device side. And this of course works. I mean, we have NR on millimeter wave all up running and so on. But here I think it's also an area where we can further enhance the performance, and especially if we as we go to even more number of antennas, it of course is both a complexity part itself, but it's also about finding good concepts and good ideas on how to do beamforming and make, what to say, both beams to find each other, so to say, as efficient as possible. And in here we should of course also recall that one thing is of course once you already had found the beams, and it's more about tracking the beams, and as the devices moves or environment changes, you need to find new beams and so on. But another aspect of this is of course also when you have the initial access, and how you are able then without knowing where you have the devices radio-wise and so on. So I think this is also an area with some opportunities for further enhancements. Okay, so this of course looks like a quite big challenge, 11 to 42 dB link budget challenge. But I thought also at the same time we can have a look a little bit how does it actually work on millimeter wave. So I will start with some simulations that were made. So this is simulating basically a macro deployment with high band. And the hypothesis here is a little bit that you need to start with the deployment that is already out there. So what happens then if you deploy a millimeter wave band? And also in the results, we basically play around with being able to both have an LTE network on the lower frequencies and then an NR system both on midband and high band. And then best guesses on bandwidths, of course, those can be changed and a little bit different depending on scenarios. But I think all the assumption here is try to be as reasonable as possible where we are today or maybe tomorrow. especially when it comes to the output power, as I said, that it's a challenge. So there are some assumptions here, and they are of course very valid for the low and mid band, maybe a little bit positive on the millimeter wave side, but we'll be there tomorrow. So then we have taken, in this case, a map of London. We have imported it into the simulators. We have put out the base station. The intersite distance here is around 450 meters. And here it's only the millimeter wave deployed. So what happens then? And then we have users here where 80% of the users are indoor, which is a fairly reasonable assumption, and we have 20% outdoor. And then you see at the map, basically the dark green, that means of course good. Red is not so good, but still in coverage. And the light blue actually is where we are not able to provide coverage. And there you basically see that, yes, there are especially indoor buildings where it's not possible to get the millimeter wave coverage. To the right, you have basically the CDF of throughput among all these different positions then. So the red curve there, that's for the outdoor users. And here we see that, yes, it works actually really good outdoor. So basically 60% of the outdoor users, they have at least 500 megabits per second, which is good. But it's much more challenging for the indoor. So the yellow curve here, that is the sub-selection of only indoor users. And there you see that it's only 15% of them that has more than half a gigabit. And if you go down to the 50th percentile, you see that it's hardly even 100 megabit. So indoor is definitely a challenge. But here also comes then one additional thing we can play with, and that is of course to be flexible in spectrum and how we actually combine different frequencies. So this is what you get if we, in this case, turn on also midband, both 2.6 and 3.5, and even a low band. And there you see that basically the full area, including indoor, becomes dark green. And the reasons are twofold. Of course, first of all, the lower frequencies has better indoor coverage. So places that before were uncovered basically are now covered. And the other thing that happens, that is of course that everybody that can use millimeter wave, they do so, and by that offloads the midband and the low bands, and thereby also decrease the interference level in the network. So here you see a completely different CDF. So here 90% of the outdoor users are above 1 gigabit, and 50% of the users are also above 1 gigabit per second. So this also turns out to be a very powerful use. So I think we should think also in the spectrum domain and how to utilize spectrum in the most efficient way. That I think is also one key ingredient going forward and further enhance performance. Okay, so these were simulations. So then I also want to share a few measurements. So these are made at 28 gigahertz. It's like a macro urban suburban scenarios. And the three different graphs are for three different sites. And it's also, the scenario is like a mix of line of sight and non-line of sight. And then you have the blue line in the graphs, and this is actually the noise floor for the measurement equipment. So any values smaller or below the blue line, we cannot trust the absolute value, but yeah, obviously they are below the blue line. And but one should also note that the blue line, if we take some assumption from the same assumption as in the previous when it comes to output power, antenna gain, put together link budget and so on, basically the blue line corresponds to, for if you either assume a fixed wireless kind of antenna gain, then it's 1.6 gigabit per second in downlink and 110 megabit per second uplink. So that might, being below the blue line might not mean the same thing as being out of coverage. But that's definitely some quality, some kind of quality limit. And what we see then from the measurements here, that is that the simulation and so on are very well aligned, that you see that you basically have very good outdoor, and I should also say that this is outdoor, so it's drive testing. So, so this only includes outdoor measurements. But you also see that outdoor, yes, it works very good. So up to 300, 400 meters, you basically have very promising path gain. A little bit interesting side result of this is that you also see some red dots actually above the free space path loss, which of course you can question, you know, how that come. But our findings there is that it seems like that's where you have actually constructive multipath. So it's probably strong reflections and so on that actually adds up to this this very good spots. Okay, then I also want to flash that outdoor coverage seems very good. Then of course one part is also trying to extend the range even beyond normal urbanish ranges, and here we have made a joint trial with Qualcomm and US Cellular, and actually showed some potential even stretching the distance up to 5 kilometers and maintaining a speeds more than 100 megabits per second. So I think this is also a sign that, or it's a strong indication that that playing with antenna and deployments actually it can enable a lot of different use cases for the millimeter wave. But this is relying then, as you see, on a fixed wireless access like terminal, so you have additional antenna gains here. So to summarize, millimeter wave are definitely used in deployments, and it's definitely very efficient in if you have kind of good coverage kind of deployments, like line of sight to buildings, small cells. You are outdoor to outdoor or indoor for that sake, and also fixed wireless scenarios. And we also see that even reusing a little bit these kind of macros typical site densities, and or maybe with US measure it's probably more in the dense macro, but talking hundreds of meters between installations, that provides very good outdoor coverage. We also, I didn't show it here, but we also done measurement outdoor to indoor, and that works as well, but you have to be a little bit more careful with the deployment, and you need to really make sure that the buildings are illuminated from the base station, and then, as we also saw, the combination and being able actually to use different bands, that is very powerful and important to get overall good network performance. So looking a little bit then into the opportunities and where additional, I think, enhancements are possible, areas like output power, antennas, these beamforming concepts, also how to play around with deployments are very interesting. And also, I think from the last presentation, I think also channel coding we should continue to work on. So by that, I conclude my talk, and I hope we have some time for some questions as well.
Thank you, Mikael. So we can have a couple of questions. Let me see what we have so far. So yeah, there is one question for you. For the 5-kilometer trial, did you use hybrid beamforming or fully digital? How much is the EIRP?
This is hybrid beamforming. I think we are at least in this first version of products and so on at millimeter wave, due to those are hybrid beamforming concepts. And regarding the EIRP, I have to pass on that one. I don't know it by I can check it up, but it was basically a normal base station.
Okay, thanks. So there's one more question about the simultaneous user total capacity you expect to achieve with millimeter wave base stations of coverage up to 1 kilometer. That's from Dan Kilper.
Yeah, that's a good but also a little bit tricky question, since it will require quite a lot. Since we are relying on beamforming here, it will require it will depend on the user distribution in the cell. But thinking of a fixed wireless scenario, for example, you probably don't find so many users in the exact same kind of direction from the base station. So there you can find fairly good opportunity to serve many users. And then of course you also can rely on some time multiplexing opportunity.